In this video, we're working on Chapter 1, Section 6, the 4 ways to solve an equation. So, when we're working with equations, there are 4 main strategies. They're called inverse-reverse, zero product rule, quadratic formula, and guess and check. Again, those 4 strategies for solving equations are inverse-reverse, and I wrote that one down. I was getting ahead of myself a second ago. The zero product rule, also called the zero product property. Then we also have the quadratic formula. And lastly, we have guess and check. Now, we don't have enough time today to go over all 4 of these strategies in depth, so we're going to focus primarily on just the first 2. What are inverse-reverse? What is the zero product rule? Feel free to pause the video if you need more time to write, but we will move on. Okay, here is our first example to work with inverse-reverse. Recognizing that writing down inverse-reverse a lot is fairly time-consuming. From this point forward, I'll just refer to it as IR. I'll still say inverse-reverse, but with the writing, I'll have just IR. Here's our first example. How do you solve this type of equation? In class, Evan told me minus 3, which would give us 2x equals 18. From there, Nicole told me to divide by 2, which gives us x equals 9. Absolutely correct. What I would like to ask, though, is how did you know that's what you were supposed to do? How did you know the first thing you were supposed to write out was subtract 3, and the second step was divide by 2? Now, of course, I'm sure in your earlier classes when you learned how to do some equation solving, they gave you some type of a mnemonic, just some way of recognizing the steps that you were supposed to do. I'm betting that they never showed you function loop diagrams, though. And that's the strategy that I would like to show you now. And so that way we can see just the structure behind the problem. And it will give us another tool that we could potentially use, not required to use, but potentially use for some more complex problems a little bit down the road. I'd like you to consider what's being done to the argument here. If we're treating this like a function f of x, what are we doing to it? What's step number 1? Okay, so step number 1 is to multiply the argument by 2. When you take x times 2, what do you get? 2x. After that, what was the next thing we did? After that, our next step was to add 3. When you add 3 to the 2x, the step before, you get 2x plus 3. You notice that basically what we're doing right now is we're just building the function in stages, looking at the order of operations to see what's happening with it. Inverse-reverse is about working backwards to solve. In this particular problem, when we were looking at it saying it's equal to 21, in order to solve it, we just have to say, start at the back and work your way toward the front. Because we already have the image, we're trying to work backwards to get the argument. Well, how do you undo add 3? Subtract 3. How do you undo multiply by 2? Divide by 2. This is a function loop diagram. It shows how to build the function following the order of operations and how to solve it based on using the inverse operations in the reverse order. Remember, inverses are operations that undo each other. And so our name of inverse reverse is just about undoing in a backwards order. Okay, resuming the video. One of the key components of inverse reverse, it only applies if you have a single occurrence of your x variable, a single occurrence of your argument. Consider example number 2. Pi times x equals 5 plus x. In this problem, we can see we actually have multiple occurrences of our x. But it's the same type of x. It's just plain old x. It's not x squared or x cubed or square root or anything weird. It's just a regular old x. This is still an inverse reverse problem. We can still solve this based on a function loop diagram. The task that we have to set up, though, is we have to combine the like terms. We have to consolidate our like terms so we have just a single occurrence of the x. Please notice then what I could do is subtract an x over on both sides, which gives us pi times x minus 1x, putting in the typically unwritten 1. From here, we could use the distributive property to factor out the x, which leaves behind pi minus 1. And we can see, after using the distributive property, that this is a piece that has a single occurrence of x, and in this format, it easily fits our inverse reverse. To build the function loop diagram for it, again noting here is our function. Oh. What's being done to the argument? What is the parentheses with pi minus 1 telling us to do? We know parentheses. Yeah, you got it, Ryan. It's just telling us to multiply by the quantity pi minus 1. And that's really just a simple one-step function. So how do you undo the multiplication? With its inverse, division. Thus, here's a problem. Check it out. There we go. In order to solve this problem, all we need to do is divide by pi minus 1, use the inverse operation in reverse order, and we get something that we could then plug into our calculator. 5 divided by the quantity pi minus 1. Which, of course, we want to round to 3 significant digits. So let's grab the calculators and check it out. 5 divided by pi is located above the exponent key on the right hand next to clear. Since it's in our blue, we'd have to use the second key to access the pi button. Please notice I'm not putting in 3.14. I don't want to round in the middle of the problem. And so we wind up with our answer, which will round to 2.33. Wow, that is a horrendous looking 3. Okay, Ryan asked about this stage in particular. Where did this stuff in the yellow come from? And it was based in the distributive property. At this stage here, I looked at it and said, what do they have in common? Both the pi x term and the minus 1x term have an x in common. So that is a piece that I could factor out. If you take out the x, what got left behind? Pi minus 1, which is how I obtain that for our equation. That help clear it up? Okay, we'll take one more example for inverse-reverse, and it will have a little bit more complexity. Solve this function. Use a function loop diagram to help map out the strategy. So here's where we will begin. And I need to extend this and bring it back up. What is the first thing being done to our argument? Okay, so we're cubing it, which gives us x cubed. What was the next thing that was done? Thank you, Brian. Subtract 1, which gives us x cubed minus 1. Then what happened? Divide by 4. Thank you, Dylan, which gives us x cubed minus 1 divided by 4. That has mapped out our entire function. What will we need to do to solve it? Use the reverse. Inverse operations, reverse order. To cancel out and undo divide by 4, multiply by 4. To undo subtract 1, you add 1. To undo a cube, you will need to take the cubed root. And so this tells us exactly what we need to do. Our process then is to say, since this whole thing is equal to 13, and especially if we're going to be using the calculators and not writing down steps, if you're not required to write down the steps, this is a nice way of being able to do it, because we're just taking 13 times 4 plus 1, and then the cubed root of that. So grabbing the calculator, and I realize, of course, we could do this, a lot of this work in our head too. 13 times 4 gives us 52. That answer plus 1 gives us 53. Our next step is to take the cubed root. With these particular calculators, you need to keep in mind and remember how to take cubed roots, or in particular, if you take a cube, that's an exponent of 3. To take the cubed root, your exponent is the reciprocal fraction, which is 1/3. So to put that into our calculator, we can take that answer and raise it to the 1/3 fraction, which gives us our answer. Round that to 3 decimal places, or not 3 decimal places, 3 significant digits, 3.76. And so Here's our answer. X is equal to, or approximately equal to, 3.76. And this function loop diagram is a completely valid way to write up your work, to write up the work. I'm sure with a lot of your previous classes, you would have worked on solving this type of thing by taking times 4, giving you x cubed minus 1 equals 52. Then add 1, x cubed equals 53. Take the cubed root and get x is equal to 3.76. I'm sure that's how you would have had your work written up in earlier previous classes. There's nothing wrong with writing it up that way either. It's completely valid. The function loop diagram is just an alternative way to write up the same work. The thoughts behind it are the same, even if the writing is different. That makes sense? Okay. The second strategy that we'll talk about today, and then we'll finish off with this particular video. In our future work or future videos, we'll look at the other strategies. But we also need to look at the zero product rule. Again, this is sometimes called the zero product property. In fact, it's more commonly called the zero product property instead of rule, but the name's less important than understanding what it is. Basically, if you are working with real numbers and you have a product of real numbers which equals 0. You can see why it's called the zero product property, because it's a product that equals 0. If that happens, then one of those things has got to be equal to 0. There's just no other way around it. Using some perhaps silly examples, you take 3 times 5. Do you get 0? No, you get something that's not 0. You take 12 times negative 3. That's not 0 either. But if I said 6 times question mark is equal to 0, what do you instantly know? It has to be a 0. The only way to have two numbers multiply and give you 0 as a result is if one of them, or maybe both even, but one of them has got to be has to be a 0. That's all the zero product property is. Now, when you're working with numbers, that seems pretty silly, but when you start working with variables, it becomes a very, very powerful tool for us. In fact, along with inverse-reverse, it is one of the main strategies for solving equations. Consider this example. Here are two numbers. The number x plus 2, x minus 2, the number x minus 2 being multiplied by the number x plus 3. Those two numbers multiply to equal 0. Because we have a number multiplied by a number equaling 0, the zero product property tells us right away there are only two ways that this could possibly happen. Either that first number, x minus 2, is 0, or the second number, x plus 3, is equal to 0. Either way, it breaks this up into a simpler set of equations, which we can solve pretty quickly. What are the answers for your first one? Positive 2, or generally speaking, this is a strategy that gets introduced for most students in Algebra 1 and is heavily reinforced, becomes a significant tool. You use it a lot in Algebra 2. My expectation is that you've worked with this and are fairly familiar with it. Generally speaking, Algebra 1 and Algebra 2 tend to focus on this a lot because of factoring. All the work that you spent factoring in Algebra 1 and Algebra 2 were designed just so that you could learn how to set up a problem that works for the zero product rule. Tell me what we would need to do to solve this one. Well, we'll consider first number equals 0 or the second number equals 0. So what are your solutions for the first equation? Okay, what are your solutions for the second equation? Got the answer of x equals 2. That's incomplete. There is another number that makes the second one true. In particular, if we did add 4, we'd get x squared equals 4. And when you take the square root, remember to take the positive and negative square root, giving you positive 2 and negative 2. Completely valid way of solving this particular problem. I'm about to erase this work though. So if need be, pause the video, finish doing the writing. I would like to note though, we could have factored this more. One of the expectations for this problem is that you would recognize the difference of squares, x squared minus 2 squared. And therefore, that's a piece that we could split up with the difference of squares formula. As Ryan noted, x plus 2, x minus 2. And so we have this completely factored. In this instance, we have 3 numbers being multiplied to 0. The zero product property, or the zero product rule, still applies. One of these numbers must equal 0. Again, I want to emphasize the first way we did it is completely valid. There was nothing wrong with doing it that way. I'll admit this is my preference. I mean, you spend all of Algebra 1 and Algebra 2 working on factoring. Why not use those skills that you worked on for 2 years? With 2 years of effort in factoring, why not take advantage of that? You'll notice, of course, in that instance, we still get the exact same answers. Negative 4, positive 2, negative 2. Consider this one now. Those first ones I gave you, they were already in a factored form. This one's not. So it does not look like it fits the zero product rule because it's not two things being multiplied to equal 0, but this is something that we could manipulate and get to work. What is the rule for factoring? We're looking for two numbers that multiply to negative 4 and they add up to positive 3. What are those numbers? Positive 4 and negative 1, so x plus 4, x minus 1 equals 0. And I wanted that to be in black, so let me change the color. According to the zero product property then, x plus 4 is equal to 0, or x minus 1 is equal to 0, allowing us to find the two solutions, -4 or +1. And that example is finished. Here's another one. Copied this one down incorrectly. That's supposed to be subtract 4, not add 4. So what does the zero product property, the zero product rule give us? X plus 2 is equal to 0, or the natural log of x minus 4 is equal to 0. So solve them. First one's easy, that's just x equals -2. The second one is a little bit more difficult if you don't remember some components. This one, of course, is telling us natural log of x is equal to 4. And I'm wondering, do you remember how to get rid of the natural log? Do you remember how to undo natural logs? Which is just saying, what is the inverse operation to natural log? Well, if you don't remember that, here's a theorem. Natural log of x is equal to a constant if and only if this is an equivalent form. So in order to solve this particular problem, what we have is natural log of x equals 4. The equivalent format for this, based on the theorem written in purple, e to the 4th is equal to x. And so we have our two solutions. I would like to take a second and make sure that you know how to use the calculator for these pieces. So can you enter in e to the with the calculator? And so what I'd like us to be able to do here is just, with the calculator, get these things. E to the -4, e to the +2, and then the natural log of 10. Okay, so e to the -4. Please notice the e to the button is located above the natural log on the left-hand side, next to the 4. And since it's in our blue, we'd have to go second, e to the x, -4. Hit enter, and we have our value. Rounding that to 3 significant digits, 0.183. E squared, we'll go e to the power of 2, which rounds to 7.39. And lastly, natural log of 10. Well, it's the same button. Natural log. Don't need the shift key for it, though. And the natural log of 10 Turns out to be 2.30 when we round it to 3 significant digits. Oh, wrong one. And to finish off the video, there's one last example we'll look at. We won't solve it, but we'll just examine it. Consider this problem. What would you do? The factored form looks pretty nice, doesn't it? Because we've got our product. But that's not a product that equals 0. This whole thing falls apart. We have no clue what to do. The 0 product property right now is completely worthless. In order to solve this particular problem, if we wanted to use the 0 product rule, we would have to expand this or FOIL it, then subtract the 10 over, which would create our equals 0, try to factor it over again. Basically, I wanted this problem to be a little bit of a warning. Just because something is factored and looks nice, that does not mean the 0 product rule works. It must be a product that equals 0. Don't forget that other part. Since we have no more questions, we'll pause here, and in a future video or tomorrow we'll pick up and look at quadratic formula, which we've already done some in class. We've got programmed into calculators already. We'll see how that one works. And then we'll also do some more work with our calculators and specifically see how the calculators are really awesome at using guess and check to find answers quickly.